Okay, hi everyone. I'm back, although it took me a little bit of time to figure this out. So, unfortunately, my internet completely gave away, so it just wasn't working. So, I had to move to a different spot to make sure that I'm able to continue. Okay, so um, just give me a moment. Just connecting my iPad so we can continue with the class. Sorry, just give me one moment. Okay, so let me just first reshare the slides because um, you know, let's just recap where we were. All right, so we were on, we finished question 2, we were on question 3, and I was talking about income and substitution effects and Marshallian and Hicksian demand, right? So now this particular question is actually given for a utility function which has substitutes, it's perfect substitutes. So in this case, we can still calculate the Hicksian and Marshallian demand, and actually we will do that. Although what is asked in the question is only the value, the final answer for the demand vector. But what I wanted to discuss was, the whole thing, how you approach such questions in the first place. So what I'll do is I'll first solve the general case for what do you do when you're asked for the Marshallian and Hicksian demand vector, for a perfect substitutes case. And then I will discuss how we can derive the minimum expenditure function and how you can then solve for the Hicksian demand functions from there. Okay, so let me. So this is a question of perfect substitutes where u is equal to x plus y. There are no coefficients, and we are given that the initial income of the consumer is 10 units, price of x is 2, and price of y is 3. Now, after that, there is an increase in price of X, and then the new price of X is 4 units. So everything is assumed that everything is in the same units. So the question is, what will be the Marshallian final demand vector after the price increase? And then what will be the Hicksian demand vector after the price increase? Okay, so let me stop this share and let me share my screen from here. So I hope you can see my screen. Okay, so this is where we were, all right. Okay, so just for all of you who may have not been able to log back in because of all the tech issues, I will explain this in brief once again in the next class, just so you can ask me your questions again. And of course, you can look at the video also once I upload it. But I will take up a separate question, a slightly more general case or a slightly different form of the function again in the next class, so that you get a better idea of how you approach such questions. Okay, so let me write down the question again. U is equal to, oops, it's a bit too thick. X plus Y. Isn't there anything between this and this thickness? Okay, this is fine. All right, U is equal to X plus Y. Then you are given Px is equal to 2, Py is equal to 3, and let's say E is expenditure is equal to 10. Okay, so they have asked for the final demand vector, but before we calculate the final, let's first calculate the initial demand vector. All right, so let's write the budget equation. The budget equation is E is equal to Px into X plus Py into Y, right? So now in this case, you're given the values of X and Y. So let's plug that in. 10 is equal to 2X plus 3Y. Okay, so now what we can see is that this is the case of perfect substitutes and the price of Y is higher than the price of X. So what will the person do? Does this person have a name in this question? Yeah, it just says consumer. Okay, so what will the consumer do? So because X and Y are both substitutes for the consumer, what the person will do will be, he or she will consume only one of the goods, whichever one is more, well, whichever one is cheaper, right? The price of Y is higher, so they will not consume any Y. So this is the typical example of perfect substitutes where you get a corner solution. So since Py is greater than Px, Y is equal to 0 amount consumed. Okay, so therefore what happens? The entire consumption is only of X. Now if we plug this value of Y into the expenditure function, get 10 is equal to 2X, therefore X is equal to 5. Therefore, now what we are doing is, we are doing this is all basic equilibrium value before any price changes. Therefore, the initial demand vector is equal to 5, comma 0. All right. Now we increase the price. Now Px is equal to 4. Now we increase the price of X. So first let's talk about the Marshallian demand, and Py is still 3, right? Py is still 3. So what will happen in this case? The consumer now has again the same choice. Let's look at the function again. U is still equal to X plus Y. So the consumer still has to choose, they can choose between an X and Y, whichever is cheaper, they will choose that. Now X is now costlier. It is 4 per unit and Y is only 3. So now the consumer consumes only Y and no X. So now X is equal to 0. Now if we put X equal to 0 in the expenditure function, you get 10 is equal to 3 Py. Oops, sorry, not Py, Y. Therefore, you can write Xm by M is equal to 0, comma 10 by 3. Okay, now we have just solved the simple case how we normally approach the optimization problem, and that normal cases is what we call as the Marshallian demand vector, which is what we have just solved for. Okay, now let's move to the next case, Hicksian. Now in Hicksian demand, what is unique is that you hold the utility level constant at the initial level. So utility So let's call that as u bar. Let's call that as u bar. So u bar is equal to x plus y. And what was initial value of x and y? 5 plus 0. Therefore, u bar is equal to 5. Right? This much is clear. Any questions about this? That's why I first solved the initial case. See, the question doesn't ask anything about the initial case before price change, but it is important to solve for the initial case before price change because that is the value of utility you will use in the Hicksian demand. So u is equal to x plus y. We found initially that y was 0, therefore x was 5, and we found that the consumption bundle was x comma y is equal to 5 comma 0. We plug in these values into the utility function which is given u equal to x plus y, and that is how we got utility is equal to 5 or u bar equal to 5 initial level. Now because we are holding u bar as constant in Hicksian demand, what is going to happen now? Now the usual thing with perfect substitutes applies. That is the basic mechanics of you know whether it is you know whether it is utility maximization or it is expenditure minimization. Either way, that still holds, right? That is sort of like a non-negotiable, right? So now in this case again we see px is greater than py, therefore x is equal to 0. This is this is going to be true still. That still holds. Therefore now if we plug in the value of x and u bar into this equation, we get 5 is equal to 0 plus y, therefore y is equal to 5. Therefore if you want, you can write x h comma y h. H is a subscript, is equal to 0 comma 5. So that is your answer. That is what the question asks. This is where the question ends. Actually, the question doesn't ask anything more than this. But I wanted to also address how we derive the expenditure function and how we can derive the Hicksian demand functions, consumption functions, or individual demand functions. So now let's go back to the general case. Let's take the same function to keep the calculation a bit simple. Let's take u is equal to x plus y. We just take prices as px and py. And e is equal to x px plus y py. Okay, so now in this case, we need to find the expenditure function, which means we are holding utility constant. So let's outright, first of all, let's put u as u bar because that sort of like symbolically indicates that we're holding u as constant. Okay. Now, what is the condition for optimization? This anyway still holds in any case, which means ux upon uy is equal to px by py. I've removed the negative sign, and here when we say ux and uy, we're obviously talking about the general function. Ux means del u by del x, and uy is del u by del y. We're taking partial derivatives. Partial derivative with respect to x here is what? Actually, I think we may have taken a slightly different value. Just sorry, give me a moment. Yeah, so ux is just 1 and uy is also just 1. So px by py. No, sorry, let me rephrase this. Actually, I've taken too specific case. Let's just take this as a slightly more general function. Let's take this as ax plus by. Okay, so actually I had solved it with a slightly different function, and I don't think we can do this with the perfect substitutes case, because the thing is that our budget function is always sort of going to be, linear at our level. So then we are always going to get a corner solution. So it's not a straightforward thing to calculate the budget function, because it's not like a linear composition or something like that. So let's do this slightly differently. Let's take a general case um, of calculating the Hicksian demand function and expenditure function. So let's take a utility function of the type a x y, something like that, right? And prices are as usual px and py are the prices. Okay, and here I've taken the exponents as one, just for just so we can make our lives a little bit easier. But you will take the same approach if you want to do something like a Cobb-Douglas function or some other function. Okay, and e is equal to x px plus y py. Now we can do the same thing. Yeah, actually, I'd taken this function, but by mistake, I started with the perfect substitutes case. Okay, so we do the same thing. Ux by uy is equal to px by py. I've removed negative sign from both the sides. So ux is nothing but ay, uy is nothing but ax, so to px by py. A gets cancelled. We can say y py is equal to x px. Okay, now most books you will find that they don't do this in this way. They use the Lagrange multiplier method, and you can of course do that, but I somehow find that to be a little bit unnecessarily complex. This is doing precisely the same thing. It's just a slightly simpler and a more intuitive approach, which is why I like to use the MRS method. But of course, if you prefer the Lagrange multiplier method, or if the functions are a bit more complicated or something, you can use that method also. So now we got a certain relation for between x and y in terms of px and py. Now let's number the equations. Say suppose this is equation 1, this is equation 2. Let's plug in these values back into the expenditure functions. So E is equal to, say suppose I substitute for y py, you get x px 2 times. So this is just 2x px. Now from here you can just write x as equal to E upon 2px, and similarly, instead of substituting for y, we can substitute for x, and you will get y is equal to E upon 2py, right? This is not too complex or dense so far. Okay, so now we have derived certain functions, the individual demand functions for x and y, right? This is how we normally derive the um, demand functions. I'm not talking about the actual values of demand functions. Now from here, now we know these values of x and y. So, why not kind of substitute this back into the utility function? So say suppose we take u bar is equal to ax comma y, not comma, sorry, ax into y. So then u bar is equal to a, x is what? E upon 2px, and y is E upon 2py, right? So now we can rearrange the terms to write it in, or to write the whole thing for E in terms of U bar instead of U bar in terms of E. Now see, what we've done is we've replaced all the X and Y's and we have just gotten it in terms of the parameters, where Px, Py are parameters, A is a given constant, and U bar we are taking as constant also. That is why it's Hicksian demand, right? So this is what U bar, this is 2 into 2, 4 U bar, Px, Py upon A. This is E square. Now, of course, all these terms here, let me also specify A is always greater than 0. So, I mean, I haven't mentioned it here, but that's almost assumed that that's given that A is greater than 0. So we can just take square root 2 under root U bar Px Py by A. This is your expenditure function. This is what we generally do. So, I mean, don't worry so much about the form of the function and what values we are getting, because anyways, I've taken this in a slightly general terms. I've taken the exponent as 1 for x and y, which sort of simplifies the calculation. But if you're given x to the power alpha, y to the power beta, or something like that, you will still take the same approach. You will just get some more numbers here and there, some more constants here and there. Or this may not be a Cobb-Douglas, it may be like a quasi-linear function or something like that. Then quasi-linear, you have to check if there is a corner solution. If there's no corner solution, then you can obviously do this kind of a treatment for it. So we first find the values of x and y in terms of the parameters and the expenditure function. Then we replace those values back into the utility function, where we have held utility as constant, and we simplify the whole thing and we get expenditure in terms of the constant utility. See, because remember that what we're doing in Hicksian demand, if you remember what we're actually doing here is, let us say that this is, say, your budget line, okay? And let me draw the indifference curve in a different color. So say suppose this is your indifference curve, okay? Now what we're doing is we're saying that your in reality what is happening is your budget is going to change. So what we're doing is we're moving along this indifference curve, holding the utility constant, and at some other point we are going to find the wait, let me just draw it. So what happens is we rotate the okay, I've not drawn this very accurately, but okay, let me first draw the new budget line and then we'll draw the, say suppose price of x increases and your originally it was tangent like this. Now what we're doing is we're trying to find a different line where you can maintain the same level of different point, sorry, where you can maintain the same level of utility, but you will obviously need to increase your expenditure for that, right? So this is, say suppose, the rotated budget line, and I'm like, because I'm not able to draw it very properly, let me just redraw the whole thing. The thing is, if I draw it, it's not going to come out as tangent at the correct point. That's the problem. So, okay, let's leave this for now like this. This is rotated like this, the budget line. And there is some other point where this whole thing is becoming tangent again. What you're doing is you're moving along the indifference curve. That is the main thing to remember, that you're moving along the indifference curve. You're not actually leaving the indifference curve. It is just that if you want it to be tangent at, you want to sorry, let me rephrase that. You're moving along the indifference curve, so you're holding the utility constant. So if you want to maintain the same level of utility with increased prices, you will obviously need to supply and supplement your income, right? Because at the new prices, your original income is not going to give you the same level of utility. So, which is why we call this as compensated demand, because if you want to hold the same level of utility, which is the basic defining characteristic of Hicksian demand, that you're holding utility constant, you're moving along the indifference curve. So if you want to hold the same level of utility and you want to allow increase of prices, then you obviously need to compensate your income, which is why we're trying to calculate the expenditure function. We're trying to find the expenditure function which minimizes your expenditure given a certain level of utility and prices and blah blah blah. So that's what we're trying to do over here. Okay, so now what we need to do further from here is calculate the Hicksian demand. Let me see if I can continue with the same example. So basically, what the Hicksian demand is not that straightforward actually, but I'll still discuss it because I think it's, again, I'm not even sure if this is actually going to be asked in your um, assignments and stuff. But let me just touch upon this part anyway, because the maths was discussed in the class, but I didn't see any question on it. So let's talk about the Hicksian demand. So you derive the Hicksian demand, say suppose for x, by taking a partial derivative of the expenditure function with respect to px. Or if you want to take it as good 1 and good 2, you can take it as, q1 and del e by p1, or you can use whatever notation you like best. Now here e is a function of u bar, px and py. You have to remember that this e is not the e we had in the original equation pxx pyy. This is not that e. This e is a function here, and it's a function of u bar, px and py. So please don't make that mistake, because sometimes people think, oh, x is a the demand for x is partial derivative of e with respect to px, and if you apply that in the original expenditure function, of course you'll get x right back, but you won't get the function, right? Okay, so in our case, x is equal to del by del px of 2. Let's take everything else. Let's write this. Let's write all the constant terms separately first, into root px. Now, what is the derivative of root px? 1 upon 2 root px, right? So the two get cancelled. So this becomes u bar py upon a px. Questions? I've just taken the derivative, that's all. This is like, I've separated out the terms which are constant, and I've just taken the derivative with respect to px here. Similarly, you can take y is equal to del e by del py. Again, let me clarify here. It is a function of u bar px and py. So y is equal to, we'll get a we'll get a similar result here. U bar px upon a py. All right, I've just cut it short. I've just taken the derivative of this function with respect to py. With the derivative is of root py is 1 upon 2 root py. 2 gets cancelled, and I just put py back into the back under the under root sign. You get u bar px upon apy. Let's put this notation correctly. This is your Hicksian demand. So this is how you get the Hicksian demand functions for two goods. We're not going to discuss the case of more than two goods anyway. So this is just a pretty simple thing. And this is the method. So you have to first get the expenditure function, and then from the function, you just take the derivative of the function with respect to px and py, or p1, p2, whatever you're using, and that gives you the Hicksian demand function. Okay, and now remember that this is not something you can do directly in the perfect substitutes case, because in perfect substitutes case, it's a corner solution. So you won't get such a neat little expenditure function out of that case. And so in the case of perfect substitutes, you will solve it the way we solved it before, that you just solve it using your basic intuition. You see which price is higher, that good will be consumed in zero quantity, or that good consumption is zero. And then you see after the price change which price is higher, and that goods consumption is zero. So you hold utility constant and you just calculate the consumption quantity of the other good. Okay, questions so far? So this is, I think, going to um, cover your sorry, not cost, budget minimization and Hicksian demand, and how do you address that. And Marshallian is what you normally do. I've already talked about the Marshallian demand, and I think if anybody has any confusion, we can discuss the case of Marshallian demand also in the next class. We can take up an example, and the Marshallian demand is actually the simpler one. That's why I didn't discuss it today. Marshallian demand is the simple, straightforward utility maximization method we normally use. Hicksian demand is little bit slightly roundabout, but I think it's still a part of the syllabus, so I wanted to discuss that today. So, any other questions? If not, then I think we can probably end the class here, and I will see you again in the next class. So again, apologies for the tech issues. I had to reconnect, move to another location and reconnect back and record it. And I have just, finished the content for this week. I will upload this video, and next week we will continue from here. Okay, thank you everyone for joining, and I'll see you again next week.